Alrighty, hello everyone. So tonight, Matt and I, we work on the same team at Netflix. We're on the Edge Services team, which means we're the team that handles all the incoming traffic and the web services for all the devices. And my intent tonight is to, in the first half, when I speak, before I hand it off to Matt, is to give you an understanding of what Rx is all about, what we've done to bring it to the JVM, and to Scala more recently, what's been going on in that space. I will be up front that I am not very skilled in the Scala side. That's why Matt's here to make sure I don't make a fool of myself. I predominantly work on the Java side and then mess around a lot in the Clojure, Groovy, Scala, polyglot space all around the edges. So what I'm going to be doing is going through the more polyglot nature of Rx. All the code is in Scala I'm going to be showing today. And the intent is to show how we ended up choosing to adopt a reactive programming style, why we ended up doing so, and then walk you through some of what that looks like, and so that you can hopefully come away from it with a better understanding of functional programming styles applied reactively without needing to worry about the category theory and monads and those types of things. So what it's all going to ultimately be about is how do we compose these functions but do it in an asynchronous way. And so as we take streams of data, how do we do this in such a way that it's non-blocking and we can react to these flows of data as they're flying by? And so we have, back up one, we have kind of been calling this functional reactive before I ended up stepping into the 20-year history of what FRP stands for. So I'm going to try and bow out of that whole argument over what functional reactive stands for. But we use it functionally in the sense that typically they're mostly pure side effect free functions. Typically these are taking the form of lambdas or closures. And we're applying these functions reactively to data as it's in an asynchronous or concurrent approach as behaviors, values, and events are flying by. And so these are the kind of the two principles. Reactive processing with functional principles, because you can do reactive programming in a fully imperative manner, but there's a lot of value in combining the two together. RxJava supports these 5 languages, and then as of yesterday added a new one, Kotlin, from IntelliJ. And so Java 8 is going to be a pretty big deal. Java 6 support is where the library strives to stay at, so that we can support Android. So Android, despite the verbosity of anonymous interclasses, they have actually come to quite like this library. But today, all the demos I'm going to be giving, all the code examples, are all going to be in Scala. We typically, in our production environment, are using Groovy for a variety of reasons. But Scala is obviously the focus of where we're at today. And so what RxJava is it's a library for composing asynchronous sequences or streams of data. Those sequences can be in the shape of event streams, or it can be a single request response that's done asynchronously. They can be behaviors, such as a metric or a mouse event or something like that, that is just constantly flowing and you can take snapshots of it. Or it can be something where it's actual discrete events where you don't want to lose the data. Whatever it might be, Rx is a library that allows you to compose these with higher order functions. So Netflix, we do movies. You should know that. You're in San Francisco. We are in lots of places now, and our API has been growing a lot over the last couple of years. We're past the 2 billion a day mark, and all of those calls are coming from the devices. There's over 1,000 different supported devices that we do. And they all come in through that web service layer. And so this is everything from your game systems, PS3, Xbox, whatever, to Android and iOS devices, to the little Roku devices, to the new smart TVs that you'll all be buying this Christmas. And all of those different classes of devices are all using the web service for the discovery process, everything that powers user interface, up to the point where it negotiates the manifest of where to then go get the video streams, the DRM licenses, and then that device takes that information and goes off and talks to its closest cache. And at that point, it stops interacting with the API. It goes off and works with the video files on the local cache, and then when you hit stop, then it comes back to the web service. So the web services are everything up to the point where you hit the play button and then stop button onwards. And then a little bit in between, we have a heartbeat that's ticking along, just telling us that you're still there. And so we use that to keep your bookmark of where you're at. So that's give you a little bit of context as to where this fits in, as I explain why we ended up choosing it. Behind that API, there are lots and lots of machines, all hosted on the Amazon Web Services. And it breaks up into several dozen different systems within a service-oriented architecture. And so at any given time, when a request comes in, it's between 5 to 20 network calls that are made for any single request from a device that we're making out into that back-end system. And that's from us out, and then it becomes an explosion of the call graph behind that. So 2 years ago, we were a very typical Java web app. It was totally imperative Java code base. It was like anyone could walk off the street with Java experience in building web services, and they would recognize the model. It was Rustlet style, Jersey style web services, and it had become a horrendous mess because it wasn't just mobile and desktop we were trying to target. It was a dozen plus different classes of devices that each had all their different semantics to adjust for the data that they needed for their use case, their screen real estate for the processing power on a different machine. And so the number of parameters and flags and expand keywords and all these things that were being passed into these RESTful APIs made it so they were no longer really all that RESTful. And we realized that we needed to change something. The other problem was that it was really inefficient for the devices because REST, a typical RESTful model, is a one-size-fits-all approach to device management, and you try and have a very fine-grained, resource-oriented API, but what that means is that your devices are then picking and choosing all these fine-grained APIs to compose user experiences. So what that meant is you launch a device, and you might end up making 12 network calls over your slow, horrible Wi-Fi network or a mobile phone, and the WAN latency on every single one of those calls was present. And so we realized that we needed to come up with a way to look a little bit more like this, where the resources we were exposing were use case oriented rather than resource oriented. And so instead of representing a particular data set, we needed to move to a model where we represented the use case that a given user interface was trying to target. But that actually differs widely between something you carry in your pocket to a PS3 or your browser or a Roku device. And so the decision we had to make was, there's a few things, but one of them was, if we're going to collapse all of this, we had a lot of the concurrency, the parallel execution just happening naturally because of all these separate network calls that could happen in parallel. So we wanted to push that all server side. A lot of benefits from that. We got to take advantage of the much better processing power of the server hardware versus $40 silicon in a Roku device. We also got to reduce a lot of the duplication between calls. On every single call, you're authenticating, you're fetching user metadata and all those things. So you could reduce a lot of that. And it simplifies the programming model a lot for the clients. And it means that you're doing one network call with paying the latency cost once, and you can also optimize the data that you're sending down server side before you get it down, so you can reduce the payload of data that's coming down the wire. But what this meant is that we all of a sudden now had to explicitly be managing concurrency, whereas before you could have just a bunch of network calls happening independently of each other. We now had to explicitly manage all of the concurrent execution and a lot of nested conditional logic. And we also didn't want a single team to be doing all this because they would become the bottleneck. So Matt and I, we work on that Edge Services team. We're a fairly big team, actually. We've got 22 of us split into 3 groups. But even at that size, we would become a bottleneck for the whole company if we were the ones that were going to go and optimize the web services for every single one of the class of devices. So we wanted to allow all the UI teams to build their own web services on top of us. And we're a very polyglot environment. We have a lot of different languages, and the skill sets of the various UI teams typically are derived from whatever device or platform they're targeting. So the ones that use HTML5 and WebKit and those things, they'd prefer to work in JavaScript or something similar like Groovy. If you're on iOS, you're coming from Objective-C or HTML, depending upon what flavor you're doing. Android is Java, the .NET platforms. And so we have all these different languages and skill sets. And as much as I love this book, not everyone should have to read it in order to accomplish something. So this sits on my desk, but it shouldn't have to sit on the desk of the other 100 engineers who are going to be building web services on our system. And last of all, we needed the API to retain control of the behavior of the system, all the resources that were being used. We couldn't have it so that every person who deployed a web service was making decisions about thread pools and timeouts, and is this going to use a queue or NIO or blocking IO, and all those decisions. We had to completely abstract those away and free ourselves up to be changing those implementation details without running around changing all the web services that were built on top of us. And so what this meant for us is that in our service layer, in that Java code 2 years ago, everything was a method call like this. They were all blocking method calls. And so you go get data from something. Behind the scenes, that might hit a local cache. That might go to a memcache server remotely. It might do a web service call. It might do a Cassandra call. It didn't matter what it was. They were all blocking. And so this became a problem as we started to want to become more concurrent. If someone wants to make that non-blocking, what do? Do we want them deciding to new up a thread or create a thread pool and then wrap that call in a thread? And what if you have 100 concurrent requests, each doing that in 40 different implementations, all doing it in some different way? And that was definitely not where we wanted to go. And so we started exploring the typical approaches. We looked at the callback model, obviously. We looked at futures. We looked at futures of lists of futures if you have lots of things to return back or if you wanted to pretend to stream data. And so we started going down this path, and it wasn't very pretty. But the callbacks one felt like the right approach, actually, because futures, especially in the Java side, Java util futures stuff, it's horrible because you think it's non-blocking until you use it in a nested conditional manner, and then the first thing anybody does is you do a .git on it because you need to do something with it, and then you're blocking again. And in the Java world, you get a little bit better when you go into Guava, their listenable future, much better. You have listeners. Java 8's completable future is a far cry better sometime next year. And the akka futures are way, way better. They start to get right where we're going, where we want to be. But along this path, I was still very much in the imperative world at this point. And I was lucky enough that there was a colleague of mine, Jafar Hussain, who had come from Microsoft, who had worked with Eric Meyer while he was at Microsoft. He had the strong enough will and voice to spend the 6 weeks it took to get through my thick imperative Java head and convince me that there was a different way of looking at the problem. And so he started to expose to me the concepts of Rx. We knew that we were not going to be adopting C# in our environment. We were a JVM stack. It just wasn't an option. But the ideas behind it started to really crystallize and become clear as a very good abstraction for how to think about asynchronous data. And so what I learned is the dual of an iterable is this concept of an observable. Now, this is not the normal observable you think about from Gang of 4. This is like pulling the Gang of 4 observer pattern forward 20 years and making it know how to work in an async world. And so in an iterable, as you are pulling data from it, each time you pull, it's the next event. You do the has next, and then you do the next. And then the error handling is because it's blocking, it just throws. And because it's blocking, the completed event is it unblocks and you move on in your control flow. In an async world, that turns into these 3 event notifications. The onNext handler is the equivalent of the next call in an iterable. And it can be received 0 or more times, potentially infinite number of times. And then there are 2 terminal states on an observable. These terminal states are the end states at which point no further events can occur, the onCompleted or the onError event. And this is how the propagation of onError is the propagation of errors in an async world instead of throwing it up the stack, which really starts to be meaningless when you have threads or async events throughout a system. And so if we look down at the bottom, if we actually look at how you would use an iterable of string in a more modern language that allows you to have higher order functions on an iterable, such as Scala, and then you look at what an observable does, they actually look exactly the same, except that the one on the left is blocking and pull, and the one on the right is non-blocking, async, and push. And the only real difference is that for each is kind of in its nature a blocking operator. And so anywhere you would have a for each, you end up with a subscribe of some form, which is a non-blocking operator. And so what we end up with is this grid of 4 different ways of retrieving data. The first one is the single scalar response that we've all been doing since the very first time we touched code. And in this case, if we need to do something conditional on it, we fetch that data, and then we perform our conditional logic on it. It's all blocking. It's very easy to walk through with your debugger. It's very easy to reason through. But if you have that get data backed by a network call that's latent, and you need to do several of these in a nested concurrent manner, this starts to break down. An iterable, you for each over it, or if you're in another language that doesn't have such elegant syntax, you have a for loop or something of that nature. And on every single item around the list, you're blocking until that data comes in. So even if you were to have a fancy iterable that can be streaming that data from somewhere, you are blocking, waiting for it to come. And the conditional statements inside, if you then need to go make another network call, you're blocking every step of the way. Async single, so in Scala, you guys got it great. The Scala future and stuff that Akka brought over is excellent. And if we hadn't discovered Rx, we probably would have ended up in the Java version of the Akka future because it is perfect in what it does as far as having higher order functions, and it asynchronously applies functions to things and allows you to compose it all together. And so this is exactly where we want to be. The difference here is the code difference between them is trivial, except that this is now completely non-blocking. As the data comes back, it reacts to the data and applies a transform function to it. And so now that conditional logic that was before blocking is done off reactively when the data comes back. And then you can start to chain these things together, which is what we'll get into later, which is where it becomes interesting. Now, the interesting thing about observable, in Scala, they look exactly the same. In the other languages, they look rather different. But in Scala, they look exactly the same. So you go, well, why are we even talking here? The value with the observable, though, the difference here is that instead of a single response back, it can support anywhere. So it can support both scalar and vector responses. And so it ends up being a more generic abstraction on top of our data flows, so that we can support everything from a scalar request response to a batch response of multiple values, such as a stream of videos, all the way up to infinite streams of events or behaviors that we want to be monitoring. We have the same abstraction on top of them. And for that reason and a variety of other reasons that we'll get into, we at Netflix chose to adopt the observable as our common abstraction on top of all of our data access patterns. And so what we did is we went from a blocking API looking similar to that on top, though ours isn't written in Scala, to something like along the bottom that everything returns an observable if there's any chance of it ever going over system boundaries. So this doesn't mean that when you get into a POJO that we're going to be ridiculous and return every accessor field as an observable. That would be insane very fast. But everywhere where it feels like there could ever be a time, or obviously if it already does, go over a network boundary, we express that as an observable of T. The other strong benefit that observable brings for us is it is completely not opinionated about how the backing implementation works, or where the asynchronous behavior comes from, or even whether it's concurrent in nature. And so this one actually is completely synchronous. You could have an observable that is synchronous, and then you could flip it out and have it backed by a thread pool, or a thread pool with multiple threads that are performing the work. Or you could use an actor. Or you could have an NIO event that uses an event loop to process the data. Or you could even have a thread pool and an actor and decouple the callback onto a separate event loop. And so what we ended up adopting as our principle of observable APIs is that all of the client interactions treat the data access as asynchronously, but whether or not it's actually done concurrently is left to the underlying implementation. So the asynchronous programming model is adopted, and then whether you're actually doing parallel concurrent execution or blocking, and if it is non-blocking, how it's non-blocking is completely up to the underlying implementation and can be changed at any point in time. So now I'm going to start getting into more concrete details and code examples as to what this looks like. And I'm going to use marble diagrams similar to the top with increasing complexity as we go. And the reason why I'm going to be using marble diagrams is because they allow me to show sequences of events over time and the flow through operators. And so this very first one is showing how you create an observable. And so that first line is the actual Java method signature for creating an observable. And then underneath is the Scala code that you would use to create one. And so in Scala, using the apply behavior, you don't actually, the create becomes implicit. And as you, when you create an observable, you're passing in a function that takes an observer, and that observer in this case is going to expect to be receiving video objects. And then when this observable is subscribed to, it is going to be given the opportunity to, at that point, fulfill the contract of an observable, which is to, on next, 0 or more times. In this case, it emits a single video object, and then terminate, either through an onCompleted event or through an onError event. And so every observable has to do one of those two terminal states unless it's intended to be an infinite stream. Here is an asynchronous observable that returns a single value. In this example, I'm being very verbose and explicit in showing how I'm using an executor service under the covers to spawn a thread. Typically, in real code, you wouldn't want to do that. You'd use schedulers or some other more elegant approach. But I do this explicitly here to demonstrate that it's completely up to the observable implementation as to how it chooses to execute. It can use an executor like this if it so desires. And so in this case, it will go off and execute on a separate thread and then get some data from in a network call. And this is now happening off in that separate thread. And at some point in the future, it will call back to that observer. This is a synchronous example with multiple values. So typically, you wouldn't want to do this if this data was coming from a network call. If, however, you had this cached in memory, it may not be worth the overhead of doing something in a separate thread. And so you could just fire hose that data back if you already have it in memory. And so we have a lot of examples where we conditionally decide if the observable should execute concurrently or synchronously, because if we don't have it in memory, we'll go fetch it over a network. If we do, we'll just immediately return it back and not spend the overhead of going off on a separate thread. In Scala and Clojure, you have one other option where you can actually use async await in Scala 2.10, and in Clojure, you can use the core async channels, similar to the Google's Go routines using CSP. And so you can actually make synchronous code async without adding concurrency. Here's an asynchronous observable with multiple values that typically this would be a very inefficient way to do it, but you can do it. In a for loop, you could do a network call on each one if for some reason you actually needed to do that. And this could go until you're done, and you're not blocking anyone waiting on this observable. They just get the callbacks as they get them. So now an observer, and this is, thus far, we're not that much farther beyond what Gang of 4 does, except all we've done is we've made it async and push-based instead of pull. So we'll get into the more interesting stuff briefly. But an observer has 3 callbacks on it: the onNext, the onError, and the onCompleted. So if this get videos, I subscribe to it, I have these 3 different callbacks that are going to happen. Typically, so this one is actually reifying to the actual interface. Typically, you're going to be using more lambdas and Clojure style, so it looks a little bit more like that. And generally, you actually don't need the completed event. It's, when you're chaining operators, you need that. But if you're at the end of it, you typically don't need to know that you're completed. And so this is the core of how you would observe an asynchronous event typically. But none of that is all that interesting until you actually start wanting to compose it. If at that point, if all we had was just those two things, all we've done is just made an async callback with a lot more stuff. And that doesn't really help us much. And so it gets interesting when we start to want to compose and transform and do that type of work. And so a handful of those composable functions, there's a lot more than this. But this is a sampling of the type of functions that are then applied on top of it. So very similar to how the Scala future has a lot of higher order functions on it. Flat map, map, those types of things. Similar concepts on the observable side. And in the Scala adapter, in the Scala version of Rx, there's been a lot of effort to make the names the same. So in the Scala wrapper, the pursuit is to be idiomatic so that you can go from a Scala future to an observable, and the naming conventions and signatures should more or less be the same wherever that can be the case. So merging. What merge does is we take two or more sequences, observable sequences that are emitting data over time, and we want to take, so here we have those two sequences, and we want to take them, as those events are coming along, we want to combine them into a single one. And so we pass them through a merge operator, and that merge operator, in this case, looks like that. If you were to do this in a static way, and so like, in most of the languages, you would do like observable.merge and then pass in A, B. This is slightly more idiomatic in the Scala side to A.merge with B. And what that does inside the merge operator is it subscribes concurrently to those two sequences, and then as the data comes in, it merges them together. And so you end up with a single sequence out the other side. Another way of combining is with zip. So zip is used when you have two different sequences of different types of data. And so if you have, in this case, some data and string, you have two different types, so I don't want to just merge them together. You could if you wanted to just lose the type safety and end up with object, or it's any in Scala, right? Yeah, OK. If we wanted to ignore the typing, we could use merge. But typically, in this case, you want to do zip. So in the base RxJava, zip actually takes in a function that would tell you how to combine it. Scala's approach is a little different because you have the value types and tuples. And so zip, in the Scala side, typically you would achieve this using zip.map, whereas in the other languages you would do just zip, and it takes a function as well because it can't just assume what type it wants to return it as. So in the other JVM languages, you pass in a function, and it defines how to output this tuple. And so it would be like a function that just takes two values and returns a tuple or a pair of some kind. And in Scala, that is implicit, and then you could do your transform in a further map step.
Sorry,
yep.
Like a slightly friendlier version would be to replace pair by a case AB and then just use A and B instead of pair _1_2.
OK.
Because that way, like, you can name what the first element of the tuple is in a second.
Perfect. Yes?
Do I understand it correctly that merge can be pretty easily expressed through zip? And,
through which?
Through zip.
Merge is different because it would, merge actually is emitting each value that it receives as a discrete event, whereas zip would always, it waits for the two to come in. And so, yeah. So if you have two sequences coming in and one has received an event and you haven't received an event from the other one, it will not emit until it receives the next one. So it's zipping them together as it receives the values. Whereas merge emits on each one. So if you had one slow one, one fast one, you could emit events constantly on the fast one, and then every once in a while you receive the slow one, and it would merge it in. So that it's non-deterministic ordering on merge, deterministic ordering on zip.
So they don't have to be the same size? That's
On which one?
on merge.
On merge, no, they don't. On zip, well, they don't have to. Just whichever one completes first, you'll unsubscribe to both. So if you had one, like, you could take a finite sequence of like 10 items and then an infinite stream and zip together, and then it would reach the end of those 10, and then it would unsubscribe from the infinite stream as well. Yep. So error handling is a big deal in async, and anyone who's done callbacks will be aware of that. And promises and futures also don't do so hot if you don't have something as nice as the Scala future. And so the story around error handling is very important in Rx. And so everything about anywhere where you throw an exception in imperative code, you instead are emitting via the on-error handler, and it is carried through the entire flow of data. And so that on-error handling, at the very end of a chain, when you pass in the subscribe handler, you have an on-error handler that would receive it. And this is the equivalent to if you had a big block of code and had like the big try catch around it. This would be the catch at the very bottom of the whole block of code. And that works for the global error handling of a sequence that you've defined. But typically, you want to be much more surgical in where you're handling it. You want to be able to put the equivalent of your try catches where all the work is happening and be able to do something a little bit more appropriate with it. So on-error resume next is one of those functions. And the way on-error resume next works is it allows you to accept a sequence of events. And when an error occurs, you want to actually do something different to it. So in this case, on B sequence, not the A, but on the B sequence, I want to say if errors happen on you and only you, I want to, when receiving that on error, I want to apply a function to you. And in this case, I've passed in a function get fallback for B. And when that error occurs, I will then switch the subscription from the one that just failed, and I will turn it to the other observable that I've passed in and subscribe to that one instead and continue with that sequence of events. And so in this case, you could flip to fallback data, or you could flip to a tombstone event or an empty response, whatever makes sense for your use case. So in this case, you end up with a single sequence that combines the output of the two and ends successfully instead of emitting an error. On-error return is similar, except that it just returns a single response instead of a sequence. And then there's others such as catch, and you can like do the equivalent of like catching for different types of exceptions in a typed manner. And you can get a little bit fancier with some of those other things. But those are kind of the basic approaches to error handling in an async world. So I'm going to take you through two use cases now. One is HTTP, and the other one is how we do video lists at Netflix. And I'll end with that and pass over to Matt. So the HTTP request use case, this is an example of how with observables you can do it in an Rx manner. And so in this case, this is using the Apache HTTP async client under the covers. And we create this, and at this point it's just declarative. It's just telling me I want to go off and do that, but it's lazy, doesn't do anything yet. I convert it to this observable, which is going to give me an observable of observable HTTP response. And then HTTP has two steps to a response. The first thing I want access to is the response itself that gives me access to the header and the status codes and the header information and those cookies and those types of things. And then based upon that, I may want to continue on to get the actual content. And so in this case, when I get back that response, the content can come back as a byte array. So I flat map over it, and the reason why I'll get to the difference between flat map and map in just a little bit. I flat map over it, and then I can do a nested async call to get the actual content. And then this opens up the content stream for me, and then I get the callback as the content flows in. And in this case, I asynchronously subscribe to it after converting the byte array to a string. Now this is interesting, but this is fairly trivial. This could be done equally well with a future. There's nothing about this that requires an observable. You can go to blocking if you want. If I go up to that HTTP request that was returning a single response, and I instead flip it over to a stream that uses server-sent events, all of a sudden the exact same abstraction allows me to start receiving multiple calls on that same, using the exact same abstraction. And so now this infinite stream of data will keep emitting to me as it receives each event that it receives. In this case, I can start applying filters that make sense on a sequence of data. And in this case, that means I want to filter out everything that's a ping event, so I'm only receiving the data events. And then I want to take the first 30 in this case and then unsubscribe. And this is where we start to see how a single abstraction over both scalar and vector responses, you can apply it to both, and you have a common abstraction, common learning pattern that is applied to all of them.
Is that a continuous stream?
Pardon me?
I must say, is that a continuous stream?
Yes, it is.
You're subscribing to it. So
Yes.
take something you can,
Yep, and then at the end here, this take 30 would unsubscribe after it receives the first 30. And so what that history stream is doing, in HTML5, there's server-sent events. Server-sent events is a very simple protocol. It emits data, colon, and whatever payload you want, and then a new line feed at the end, and just an infinite stream of those. And in JavaScript, so from within the WebKit, any of the standards compliant HTML5 browsers, you can have a JavaScript listener to those. This is the equivalent inside a Java library, so you can consume that and receive these events. And so we use this in quite a few places at Netflix where we're monitoring our servers, where we'll just have an open connection to one of our servers and subscribe to an event stream as it's just flying by, and we're using SSE so that we can, so that way we have a single common standard that whether you're consuming it from a browser or a Java app or Python or whatever, it's all using just SSE to send those events out over the wire. And so this is an example of how we use an observable to consume this. It gets more interesting when you then take 1,000 servers all emitting one of those sequences, and you have 1,000 NIO connections to them, and then you merge those together through the merge operator, combine them into then scan operations to then do aggregation, and then out the other side are emitting aggregated events. And so you declare this Rx sequence, and then it just runs infinitely and just keeps emitting aggregated data events.
So you're reducing it as well.
It's not really a reduce. It's an actual aggregation of 1,000 sequences into one that combines the values together. Whereas reduce, you're typically going to be collapsing it down into a single value and then you're done. This one is just constantly churning over it infinitely, and each time it then emits the new aggregate response. So it's more like it's a scan operation. So at each step, it emits the intermediate result. So in the last example I'm going to go through is kind of the stereotypical example of why we needed something that could handle conditional asynchronous sequences of data and an approach to dealing with that. So this is the simplified version. There's another layer on top of this in the real one. But to simplify, we're just going to look at a single list of movies. In the Netflix UIs, you have a list of movies. So you have the first list that tells you all the lists, and then within each list, then you do something. So in this case, we're just going to dig into one list. And so what we want to say is, I want to go to the video service, get videos for this user ID. It's going to go off to our personalized service that has all the algorithms for personalization. It's going to fetch that back. And in code, that's what that might look like. So we go off and get those videos. And then let's say that we're on an Android device, and it really only makes sense to show 10. Instead of the 75 or 150 that we could potentially return on a bigger screen device, we're only going to return 10. And so what that does is it takes 10, and then once it's received that 10, it then unsubscribes from the parent sequence. And so the bidirectional communication on composition always has to be there in asynchronous sequences. Otherwise, if I was to use something like a take 10 on an infinite stream, I would just leave it dangling, and I would be wasting resources behind the scenes, and it would never clean itself up. The composition of Rx ensures that the entire sequence passes errors all the way down and unsubscribe events all the way back up, both directions. And so in this case, the take 10, however many things have been composed up to the origin, it will keep passing the unsubscribe up, so it cleans itself up.
Are there any other events you want to send back, like throttling or, I don't know, like...
Throttling is I'll take that after because it's a much more complicated discussion than can be had in 30 seconds. There's like 5 different ways you want to typically go about doing that. Once you get, for each of these 10 video objects, what you want to do is we want to transform them in some way. We're getting some data back, and we want to transform them into data that's ready for the consumption by the device. And so this is Groovy code, I believe, in this particular example. So map in all the different languages takes type T and returns type R. And so we want to go from map of video to something else. In fact, what we need actually, we're a little bit more complicated because we need to do nested logic, so we want to use flat map. So what flat map is doing is it's also known as map many in some places, and also as select many in the Microsoft world in .NET. But flat map is kind of the standard within most of the JVM languages nowadays, thankfully. And The difference between it and map is that it is taking type T to type R, but it's an observable of R. And so what that means is that you could be returning another asynchronous event. And then the flat map behind the scenes, all it's doing is it's the equivalent of map.merge. It takes, you map into an observable, and then it will merge over that so you get all of the events that come out of the observable that you emitted. And so it's just the assumption that in flat map, you don't actually want an observable back, you want the flattened version of it. And so the reason why we're doing flat map here is because we are going to do nested async calls. And so we're going to, for each video, we want to kick off 3 network calls. We want to go get the metadata, and we also want to get the bookmark and the rating. And so we're going to kick off these 3, but these are all done declaratively and asynchronously. And then we want to map over each of them to transform the data, again, in this nested level into whatever format we want to emit. And so this map, this whole sequence here, it will go get the metadata asynchronously. It will then reactively apply the map function to it that will transform the data from an object into, in this case, a dictionary, a map of key value pairs. And so in that map many or flat map, we then end up with 10 invocations of that on these 10 video objects. And then for each of them, we're going to do a metadata call with a map transform, and then same thing on bookmark and rating. And we want to do this all in a way that's non-blocking and that composes it all together correctly so that if errors happen, it cleans itself all up, and that if we cancel it at any point in time, that it cleans itself all up and ends everything correctly. And so at that point, all we've done is declare 3 lazy things. They don't actually do anything yet. If we were to return right there, they would never actually execute and do anything. So we compose these together. And in this case, we could use merge because we've turned them into the same 3 things. But we actually don't want a list of values. We want to combine these 3 things into one response that then we can return back to our user. And so we want to zip these 3 things together. And then we get to use some of this zip function is how the other languages work, as I mentioned earlier. We don't have to do this in Scala. Scala does it for us, but instead we'll map over it. So Scala will automatically return the combination, a triple with these 3. And then we can use the magic of Scala to handle this and return back a concatenated version of the dictionary. So what this is doing in plain English, if this doesn't make sense to you, is it is saying, please take those 3 asynchronous calls. When those 3 asynchronous calls are all complete, they could all come back at different times. When they all come back, take those 3, turn them into a triple, then hand that triple off to the map operator. And that map operator then is going to create a new map that just has the ID and video ID in it. And then it concatenates the key values from those other 3 responses into a single dictionary, a single map, and then emits that map. And so then what we have is that we're returning an observable of map at the top level of this, and we want to get 10 of them out. We want an observable that emits 10 maps out that represent each of the 10 video objects. And so the final zip emits 10 items at the end, and each of those 10 items will look like that. And so this is how all of our web services are now being written at Netflix. Over the last year and a half, all of the new device work that we've been doing is writing all of their code in this reactive manner. And this is one of the most common, more complicated use cases of building up like the main screen on one of our Netflix user interfaces. We have a list of movies, and for each movie, you need to fetch data from various different places. In our production environment, so you could do this in a very naive manner and result in 30 some odd network calls if you wanted to do it inefficiently. Behind the scenes, we're batching this into, I think we do it in 3. And the power of this abstraction is that it's completely up to the backing implementation how we do that. Metadata, we choose to cache that all on box. So even though it looks like it might be over the network, in that case, we've decided it's worth the 4 gigs of memory or whatever it is to cache that on every single box because we hit it millions of times a second. In the other 2, they are going over the network, but because we have calculated that it is better for us to optimistically fetch more data than they might use, As soon as we know that they're fetching the list of movies, we fire off an asynchronous call and fetch those bookmarks. And then by the time they come in and ask for them, it's either already done or they'll all end up just waiting until that one batch network call is completed. But the benefit here is that that's all an abstraction of how it's been consumed. And so that's the power for us, is that all the consumption of the data is done in an asynchronous and declarative manner. But then the API owners get to decide where things are actually done concurrently in parallel, what resources it's using. Is this batched? Is it not batched? Is this coming from a cache or whatever those decisions might be? And we can change it at any point in time. And we can even make it so that it's done with heuristics, so that you can say, we have noticed that this particular call path is always going off and fetching those. Every time we see this request pattern, let's just go off and optimistically fetching it, even if we sometimes drop it on the floor. But other times, we'll fetch it lazily. So we can start to do those types of things. And so we applied this at our top layer. And we figured that that's where it would stay. And the pattern worked so well for us that we started to push it deeper into our stack. And we took Hystrix, which is our fault tolerance layer, and we retrofitted it to be completely non-blocking. And it uses Rx under the covers. And so we allowed it to expose. It used to expose just queue with a future, or execute imperatively, synchronously. And we exposed observe methods on Hystrix, so that we're now getting to the point where over time, from top to bottom in our stack, we're starting to get reactive flows where from the incoming network call all the way down to our service-oriented calls and back up, we're slowly moving them more and more towards a fully reactive pattern. Looking back, these observable APIs have achieved what our original goal was, but also completely changed our approach to software. And so as we look at how we build our services now, it doesn't look anything like that imperative stack, Java stack that we had 2 years ago. All of our APIs now are observable in nature, and the reactive model, we find it's just pushing deeper and deeper into our stack. And not only has it affected our server side, almost all of our client sides, almost all of our devices now are using Rx in one of their flavors on their systems. The JavaScript Rx on all the HTML-based UIs, the .NET stack, C# for like Windows 8 and Windows Mobile and Silverlight are all now using Rx. And so they're using Rx both client side and server side, and progressively more and more in the Java-based environments. 3 things that we learned. Developer training and documentation was key. Getting people to flip their mental mindset from imperative blocking, synchronous thinking it's a mind shift for people to make. And the first couple people, it took them a month or 2. We got it to the point where now is about 2 weeks. Once you start making that effort, to enable that, we actually hired a tech writer, and it made a world of difference. Some of the best documentation I've ever seen written for an internal project. And then we forklifted pieces of that to the GitHub project that weren't specific to internal Netflix. And we have him continue to, just as more and more happens on the Rx project, every pull request he sees, he'll go and update our GitHub stuff. And that's been a really big deal to help with something that is not obvious to most people when they first come across it. Reactive programming and functional programming, both thrown together, makes your head explode if you've spent 15 years working in just normal imperative synchronous code. And there was a lot of friction at first about it. What we found, though, is once people came out the other side of that and they got through the learning curve, they wouldn't go back. Not for this kind of coding. Not when you're taking sequences of data and trying to combine them. It just becomes second nature in how we think. Debugging and tracing is different. Stepping through this kind of code in a debugger is just not the same experience. You generally don't do it. It's an area that, like Eric Meyer and I talk about this, it's definitely an area where I want to get is the equivalent of, I want to be able to do the equivalent of the WebKit inspector and point it at my production servers. That's what I want to get to. We have an idea as to how to get there. We just haven't had the engineering time to do it. If any of you want to help, we'd be happy to have it. But that's where we want to get to, because that's really what we need to be able to do, is visualize everything happening concurrently, what the time is of each function, what's going on. However, the Rx does support for unit testing the concept of virtual scheduling, and so that you can use test schedulers that use artificial time, so that whenever you're working with time-based things like windowing or buffering and things like that, you instead of real concurrency, you use the virtual scheduler, and then you advance time, assert, advance time, assert, so it makes unit testing beautiful. So you can unit test this kind of code. Just running it in production, it's the same with multi-threaded code, but it's different in production. The only real rule that we've had to state, because we work on a non-purely functional environment, the JVM is not a functional programming environment to begin with. And so even the functional languages we're using, like Scala and Clojure and things, they're not opinionated in forcing you, like Haskell, to do everything in a purely functional manner. And so you can still break the rules and mutate global state. Just don't. That's the one thing that we've just had to teach people. As long as you don't, everything goes well. All it takes is being bitten one time by doing it, and then you learn just don't do that, and life is good. In short, this pattern has proven to be very successful for us. We're seeing it move into lots of our other places. We've been using it in production predominantly for these request response style discrete events. We're now, in the last couple months, been moving a lot more into the reactive stream processing space, where we're doing it a lot more for, as we're building systems to analyze just streams of events flowing from all of our servers. That's a whole other interesting area. That's where back pressure type stuff becomes a much more important question. In request response, it doesn't matter that much, really. The infinite stream processing, it does. And so we're going to see a lot more maturity in this space, and the exciting thing about that space is that we're seeing a lot of synergy in some of the other companies that we're working with on that. A lot more information is available in some blog posts and slides online and GitHub. And I'll turn it over to Matt now, who will show you some much cooler Scala things and tell you about how we got there.
To go. So my name's Matt Jacobs. Like Ben said, I work on the Netflix team. I'm fairly new to the team, fairly new to the Bay Area. Been there about 7 months. So basically the premise of what I'm going to talk about is kind of just flesh out some of the stuff that, that Ben was working through. So Ben told us what the Rx observable abstraction is. I'm going to talk about how we implemented it. We have a use case where we have a polyglot environment. How do we manage that? So this GitHub link is full of the code that you're about to see. So feel free to play with that and monkey around with any of the observable stuff that we've been working on. So there's kind of two parts to this talk. The first part is going to be stuff that we found for library writers. For targeting a polyglot environment, what are some interesting things to watch out for? What are some good things to do? And then Ben already did a lot of this, but for RxJava consumers or prospective consumers, what are some interesting use cases? What have we found in our usage of it? So the first point is going to be, since this is obviously a Scala meetup, how does RxJava support Scala in particular? And the next bit is, how does RxJava support the other JVM languages? For consumers, how do the concurrency and collection primitives that are well known in the Scala community map onto observable? I'll show some pretty trivial code which maps things like iterables and futures onto this observable abstraction. And finally, I'm going to end up with a demo. What can I do with it? What's an example? So in order to figure out how and why we chose the implementation pattern we did, we kind of need to know, what are we designing? What are we building here? So this was Ben's talk. We have in .NET, .NET gave us a observable abstraction. We implemented it. Modulo method names and idiomatic differences. Type safety. This is a Scala crowd. I don't need to say this here. In other rooms, I would. This is not an obvious thing, and you'll see in a little bit how we kind of fell into some trouble here. We would like to support all JVM languages in a language-native way. We don't want to be newing up anonymous classes everywhere that we use observables. We want consumers to pick which languages they depend on. We don't want a Clojure shop to depend on the Groovy runtime. We don't want vice versa. Pretty obvious, but wanted to state that. Likewise, we don't want to force any decisions to be made. You can mix multiple languages if you want. You can use multiple languages if you'd like. So this is going to be the guts of the implementation. And so I'm going to start with one example of one method on the Java observable and talk about how we can use it from different languages. Scala being the type-safe example, Groovy being the dynamic example. So I think we have a marble diagram coming up here, but this is the map method, which Ben already talked about. It accepts a func1 with 2 type parameters. You can see Java's contravariance and covariance here. So we've got a func1 named f that we can map onto an observable of t. That produces an observable of r. What is a func1? A func1 is exactly what it sounds like. This is the Java way of representing that. It kind of simulates first-class functions. Here is the marble diagram. As we've seen before, we map an element of one type to an element of a new type. How do we use it? In Java, this is the syntax. This is basically the simplest possible usage of or creation of an observable. As Ben said, this could be a synchronous, observables can be synchronous values. Here we have a value of 1, and we're exposing an observable interface on top of it. Here's a map function, a dummy method where we are adding 3 to the value and calling toString on it. So we give this map a function which takes an integer to a string. Obviously, that's not the prettiest code to write. In Scala, the creation looks fairly similar. We've got a just method on the companion object observable. And of course, we have first-class functions in Scala. We'd like to be able to write them and map them back onto the RxJava implementation. Groovy, very similar. Creation, usage, looks about the same as Java. So at this point, here are the 3 methods which we would like to basically do equivalent things, living with the world that has one observable class file. How do we square that circle? So the first case, Java, done. We wrote this in Java. Of course, that works. Let's talk about the Scala case. So there's really 2 things that we need to do in order to support Scala in a way that's kind of pleasing and nice to use. So the first is we need good interop between Scala functions and the RxJava core. The second is that we would really like to use an observable in a Scala idiomatic way. That means things like apply factory methods, ++ for merging 2 observables together, cosmetic changes, drop instead of skip, zip returning a tuple. So some things kind of change cosmetically. We'd like to be able to support that and ease a transition from somebody used to the Scala native collections into observable. So restating this, we've got the Java version on top, the Scala version on bottom. The obvious, easy answer, given that we're using Scala here, is to implicitly convert a function of the type t goes to r into a func1. And this is a pretty trivial example I think most people could come up with pretty straightforwardly. There's no magic here. Given a Scala function type, we would like to get an instance of a func1. How do we do that? We implement the one method on func1 that takes an a and needs a b, and we call f of a. Pretty straightforward. So it turns out there's about 18 kind of classes of functions that are needed in order to get full coverage. We would like to always use a Scala function and never have to drop back to Java. So that's pretty straightforward work. There's a lot of duplicative code here. Macros could probably make this more concise and be kind of cool to work on. Yes?
Well, so I guess, for 2.11, at least, the compiler now supports generating that kind of code. So it'll do the same.
Yeah, we have not played with 2.11. I've read about that, so I have no...
No, I realize that 2.11 is too little too late, but for what it's worth.
Yeah, we're just picking up stuff like macros and stuff, so we haven't even gotten there yet, but
Oh.
it seems interesting.
Yeah. Careful with the macros.
Yeah.
It's not like it.
Okay, so I think that kind of covers the first bit. It's fairly straightforward given the Scala language support for implicits. The next bit we found to be more interesting. So how do we add idiomatic Scala methods to the observable class? Well, the really straightforward way is, and so this is basically the concept of extension methods. The straightforward thing to do here is to take a RxJava observable, convert it to some new class we're making up, and is Scala specific. We'll call it RxLang Scala observable. This lives in the Scala universe. And just assume that we've got some sort of constructor that can, given a Java observable, it can new up a Scala observable. And then given that you've done that, Well, let's just put all of the interesting methods right on your RxLang Scala observable. Pretty straightforward, and that's kind of the traditional way to do it. So there's two fairly minor in the grand scheme of things drawbacks. This would have been a reasonable implementation strategy. But there's a lot of times where the Scala observable would be popping out, and it's unclear how a Groovy script or Java code consumes that in all cases. There's some cost to wrapping. So Samuel Gruder, who works at EPFL, and J.M. Hofer, who's been a large contributor to this project, said, hey, let's use value classes. This would be a pretty interesting thing to do. And it turned out to really work pretty much perfectly. So for those of you who are not familiar with value classes, they are new as of 2.10. I think they actually arose kind of in the context of numeric computing and saving costs of boxing. The fact that we applied it to a wildly different domain kind of speaks to, hey, that was a pretty good idea. What a value class is it takes, let me back up, it wraps one object and basically acts as a transparent proxy for that object. So in our case, we would like our Scala observable to look precisely like a Java observable. And the syntax for that is we extend any val. What this does is there's no actual wrapping happening. These methods get added by the compiler. And since there is no other class file, it works transparently with any other JVM language. As an example of how we would use this, I have two kind of dumb examples. And again, this code actually compiles and works. This is in the GitHub project. This is an example of a producer of observables written in Scala. It does something dumb. It outputs 100 A's. But it clearly returns a Scala observable by calling producer.stream. In the same project, you've got a consumer written in Java. It has no knowledge whatsoever of RxLang Scala observable. It asks the producer for a stream of values. The objects it receives back are also of type Rx observable. It can use them without any pain at all, without knowledge that the service providing it those values was actually written in Scala. And then, of course, you call whatever function you'd like to with your new func1s or action ones.
Excuse me, Matt.
Yes?
Why don't you have to call producer dollar dot stream? It's an object, right?
Yeah, likely, you're right. That might have been a transcription error. But I think you're exactly right. The interop between Java and Scala would suggest that. So I believe you're right, and I'm wrong. So any questions on the Scala support story here before I move on? So in general, I think Ben showed the code that most of the examples he showed were in Scala, and it's a pretty reasonable functional-looking abstraction. So we've been pretty happy with how the Scala adapter turned out. I use that as a setup for the next set of topics here. How do we support dynamic languages? So the example that I'm going to be kind of threading through here is Groovy. So in Groovy, a function type is a closure of one argument. What do I produce? So if you call map with a closure of R, you will invoke that and you will get an R back. So I'm going to kind of walk through all of the different strategies we evaluated and talk about why we ended up where we did. So kind of the most naive possible implementation strategy would be, well, just throw them in the Rx observable source. Well, clearly that doesn't meet one of the goals I stated earlier. If we hand out the observable class file to anyone, they now need the Groovy runtime, they need the Clojure runtime, they need the Kotlin runtime, et cetera. That wouldn't make anyone happy that I know of. So that gets the X. So what's the next most obvious thing to do? Well, if we don't want to depend on those specific types, what is the one thing that is a super type of all of those? Object. So what if we, for every instance of a map method, we took in a func1 or we took in an object? And then if we received an object, so if we didn't receive an Rx native function type, if we received an object, anything else, well, maybe we had a static language adapter that it knew how to convert objects into func1s, and possibly fail at runtime, of course. And then, given that it has a func1, it can delegate back to the nicely typed version. And what if each specific language adapter was able to know about this language adapter static and register itself and say, I know how to reason about Groovy lang closures. Here's how you turn a Groovy lang closure into a func1. And Clojure knew the same thing, and Kotlin, et cetera, et cetera. So this works. And this is actually how we did it up until 0.11. There's a downside. It's obviously not type safe at all. Given that you've got an object that you can pass into map, this code compiles. You can take an observable of int and give it a function which goes from list of string to the list's head. That's clearly not going to compile, except it does, and it will fail horribly at runtime. So I don't need to sell anyone here on the benefits of type safety. This was a bad spot to be in. So the work that I'm about to get to removes this constraint. We're getting type safety back. So this is where it starts getting a little bit hairy. So now we're going to start talking about some static bytecode rewriting. So if we're claiming that this is a bad implementation, well, let's remove this from the source file. Let's not let this be a target for other languages to hit. Instead, let's add it to the class file. The source doesn't know about it, the class file does. Everything should be happy. So step one, we package up this source into one class file. This class file only knows about func1s. We have some code gen, and this is fairly ornate code, and it knows how to scan the class file and turn maps of func1s into maps of closures, maps of Clojure lang IFNs, maps of various native function types. Then we have another packaging step, which accumulates all the methods that the code gen created, stuffs them into the class file. So this is a pretty good spot, right? We've now got source code that looks fine. Everything can compile against that. We get type safety at the source level. The class file has the precise set of methods and signatures that we'd like it to have. If we call this class file from Groovy, that's going to work. If we call it with Java, that'll work, in theory. It turns out every tool blows up. Scala C can't resolve this class file. It will aggressively chase down every reference, and if we don't depend on it, it doesn't like that very much. And that's exactly the situation we were trying to get out of. It's not just Scala C, every IDE broke as well. So this was kind of a non-starter. It looked better on paper than after we had done those many, many hours of work to actually throw it in an IDE. So that one does not work. So this one's the hairiest of all. I'm intentionally going really quickly through this one because I mostly don't remember what I did here. This was a lot of 3 a.m. hacking here. So this is dynamic bytecode rewriting. So if there is one factory method which you are saying, I will let this factory method be not type safe, you can use that as a hook. And only at that point, you can expand an object into whatever type you want, and then you can return a dynamic observable. You hook deeply into this factory method, and you return dynamic observables everywhere. On this dynamic observable, you hook into language adapters. This actually worked, I'm really sad to say. It was impossible to debug. We were looking at calls from the dynamic observable to observable and back, and it was bad. It really only ended up working for Groovy also. JRuby didn't work. Turns out the object type of functions in Clojure has kind of a different granularity than Groovy. There's no one-size-fits-all approach to solving the dynamic language case was basically what we came up with. So this one ended up not working for a variety of reasons. So our next was to give up on solving this in the general case. So we kind of used the Scala example as a building block, and we said Scala had really nice language support for solving this. You'll notice I didn't mention Scala here. We considered that to be solved. We had the implicits and the value classes which work. So this is the good way to go. And what this means is, like we already saw, Scala uses implicit conversions, uses value classes to support Scala. Groovy, as of 2.0, supports extension modules. As of 2.1, I believe they support SAMs, which work really nicely. Clojure, something with macros. I'm not a Clojure expert, but we have somebody on our team who is and is contributing. I think there's an open pull request right now dealing with macros and Clojure support. That seems like the right thing to do, not knowing anything about Clojure. JRuby, this works now too. Extension methods, I think. I'm not sure on this one either.
Do I understand it right that you just gave up on non-type safe functions?
No, we explicitly keep the type safe core. We don't purport to have a uniform support mechanism for dynamic languages. We let every dynamic language solve it in their own language-specific way. So there is a module in our build, which is RxJava Scala, and its adapter uses value classes and implicits. There is a module in our build, RxJava Groovy, which builds up an extension module and knows how to build the jar. And we have a README that talks about how to drop that in and hook it up to your project. Oh, SAM, single abstract method. It's the new Java 8 way to support lambdas. And so it turns out that Java 8 actually works out of the box with Func1s because Func1 happens to be a SAM. Yeah, and to follow on to that point, we just received, I think yesterday, a pull request for Kotlin support, and it supports SAMs. So it worked out of the box. You can write Kotlin code, which works with our Func1s. Of course, just like we would like to add Scala native or Scala idiomatic methods, like ++, like drop, Kotlin wants to do the same, and so they're going to do some extension methods, or maybe they've already done it.
They already did it.
Okay. So long story short, one size fits all is not a great approach. Leverage each language's specific features. There's enough small nitty-gritty details that to try otherwise is folly. And bytecode generation is probably never, ever the correct solution, is one I've taken to heart. And also, I mentioned I don't know anything about Clojure or JRuby or Kotlin. I guess in retrospect, it was kind of silly to expect that I would come up with a good solution for supporting those languages. An implementation from the language community is always going to be vastly preferable than a leaky global solution. So really good lessons that we learned and I will take with me. So that's it for the library section and kind of what we learned about writing a library which is very explicitly polyglot. So now I'm going to kind of rehash a little bit of what Ben talked about and kind of how do we consume this abstraction and what does it look like. So the easiest entry point is we're all familiar with some set of concurrency constructs. How do those map onto observable? So I'm going to show those kind of straightforward implementations. So iterable, a Scala future, the Twitter util future, if you like finagle, and actors. So I think Ben mentioned this as well. The apply method takes a method that goes from observer to subscription. So in all these cases, we're going to provide a mapping between the class on top and a function on the bottom. So an iterable is a collection of elements. They're all known. This is a list in memory. What do we want a observable view of that list to look like? We want it to look like each of those elements having onNext called upon them, and then an onCompleted. That is implemented as follows. So we've got some method named toObservable that accepts an iterable of t and returns an observable of t. You can see I've kind of called out the three Rx primitives. We do the obvious thing. We iterate over the iterable, and we call onNext on each. Then we call onCompleted. Ben also mentioned this. This is kind of the inefficient approach. We can't unsubscribe here. So be it. But this is a mapping that shows how a iterable can be viewed as an observable. Next is a future. So a future, of course, is a value that might or might not be available, and it will be, hopefully, at some point in the future. What does the observable view look like here? The two cases are it returns a value via onNext and then calls onCompleted, or it throws an error, which I didn't represent here. Again, we need to implement this same interface. So in this case, and this is using the Scala concurrent future, here I'm just importing the global execution context and then mapping or using onComplete on the future. And in the success case, I call onNext immediately and then onCompleted. In the failure case, onError. Again, a really straightforward, trivial mapping. So you know futures. Now you know how to view a future via the observable lens. So this is the com Twitter util future. Really similar. The method names are a little bit different, but on success of the future, you call on next and then on completed. On the failure, you call on error. It turns out that you can actually cancel this one. So here at the bottom, this is how you would unsubscribe from the future if you just wanted to walk away. You call future, raise, new future, canceled exception. So minor differences, but again, really straightforward mapping. Actors. This is super interesting, but we don't know yet. One interesting direction is to use this kind of at the scheduling layer. And instead of using threads, map work onto actors. We've thought about this. We haven't really written code, and we haven't really come to terms on this. If you're interested at all, we'd love input from everyone in this room and everyone in the Scala community. This is some interesting directions to take our library. So open question. And I should mention, almost all this work has been done in the last couple months, and mostly not by me. There's a lot of community people helping out here. This is all not fully baked yet, so any involvement is more than welcome. Okay, so now on to the last bit. This is a small demo. This is going to be an HTTP client. So I'm going to retrieve all mentions of me on Twitter. We've got a module in RxJava contrib called RxJava Apache HTTP. I think this came in last week. And it is straightforward wrapper on top of the Apache async HTTP client. So I'm just going to put a little bit of business logic on it. So the first way I'm going to do this is via a REST call. So this is the Twitter API. I'm going to ask it for, give me all of the mentions of me. This returns a JSON blob. Of course, it returns with some HTTP code, and then it's done. So how could I represent this computation? I could represent this as blocking. This could be a sequence of mentions. So mention is some business object I'm creating here. It could be a future of sequence of mentions. This could be an async operation. Or it could be an observable of mention. In that case, I don't even know if it's async or sync. I just know that I will be getting emitted mentions of me in some fashion. So you probably see what's coming next. You could also implement a streaming HTTP client here. And that's the API which Twitter exposes. This returns an infinite stream of JSON. One of the HTTP headers that comes back is transfer encoding chunked. That tells you that this connection will be left open. How do you model this computation? The kind of two ways I could think to do this were as a stream of mentions and an observable of mentions. I'm not really sure you can model this as a future, because a future, by necessity, has a handle on something that ends. You can't grab it if it is not done. So notice, of course, the point of all this is that observable of our business object is kind of the right, or at least a reasonable, abstraction in both cases. Again, we're hiding all of the details of how this computation is done. We're just always viewing it through this asynchronous lens. So here's the actual code. So I'm defining a case class. I obviously left off all the types here, because you can probably guess what they are. And these are going to be the methods. I'm not showing the whole implementation, but if I want to get a response out, I define a method that takes a URI and returns an observable of an observable HTTP response. And so observable HTTP is one of the objects available in our contrib module. Now we've got a getJSON method. So this takes an observable HTTP response and returns an observable of map of string to any. We'll use that as our JSON representation. Obvious thing to note here is that there's really no concurrency logic inherent in this. We're just taking a HTTP response and returning an observable of JSON. A mention turns JSON into our case class in some non-interesting way. So how does this, when we put all these methods together, how does this how does this RESTful HTTP client look? So we get a handle on an observable of mention by using a for comprehension to combine, get a response, set up your HTTP response, flat map the getJSON, turn that response into JSON, and then yield you're mapping the get mention onto that map. So at the end of this, we actually get a nice stream of mentions coming out. It turns out, of course, that this was a single RESTful call. We probably got them all at the same time, but we just emit them in sequence. So when I ran this before I showed up, Alexi and bin happen to be the two most recent. And so I get 2 on next and an on completed, as you kind of expect. The really interesting thing is that for the streaming infinite HTTP call, the code looks exactly the same because we're using the same abstraction. And I think I've actually been running this the whole time I've been in here, and I think I saw a few things. Yeah, so this has been running the whole time. So you can kind of see this has been open for an hour and a half, and tweets are piling up. So the same model that supported a nice RESTful call supports this as well. So not a super exciting demo, but it kind of proves the usefulness of this abstraction. And so that's about it for the content of the talk. I did want to mention the Coursera course coming up. Principles of Reactive Programming. If you're in this room, you're probably pretty interested in this, especially given that Martin Odersky, Eric Meyer, Roland Kuhn are teaching it. I'll be taking it. I'm pretty interested. Starts November 4th. That's it.